Hey everybody, I'm Kevin Tracy. I'm one of the TAs for Optimal Control this spring. And right now I'm going to go through a quick run through of Homework Zero and some Julia installation setup and intro stuff, just to try and give you guys a solid foundation of the Julia stuff that you'll need to know going forward in this semester. So first thing we'll do is that we'll send out this link in a little bit. Right now it's private, it'll be public, and this is Homework Zero. The idea is that this should be super simple, just make sure everyone gets Julia set up and configured the way they want to. So the first thing we'll do here is install Julia. So what we're going to do is we're going to get version 1.6.7 from the Julia website. So we go over to Julia Lang, download, and we'll notice that the current stable release is actually 1.8, and we don't want this. It would probably be fine, but we're not going to use this. We're going to stick to the slightly more reliable LTS release, which is 1.6.7. And then from here, you'll go through and just grab whichever one fits your machine. And also, you're going to have some other setup stuff you'll need to do that's going to be specific to what platform you're on. So this second link, which is linked right here, platform specific instructions. I'm going to go through this, and I'm on Mac OS. So I'll scroll down to the Mac OS section. I can follow these instructions. And one thing to be careful of is that it's going to have the latest release for everything here. So 1.8, 1.8, 1.8. Make sure that when you follow these instructions, since we're using 1.6, just make sure wherever you see 1.8, we instead use 1.6. And then what we'll do is that after we download Julia, we'll have multiple different ways to open it. So on Mac, if you don't want to do any of this business, which is totally fine if you don't want to, it's actually an application. So if you go to your applications folder, you'll see in my case, I have a few different versions of Julia. So we'll open up 1.6. And this will open the REPL, or read, evaluate, print loop. So this lets us interact with Julia. And so the first thing we'll notice is that there's a version of 1.6.7. That means that we have the correct version. This is not 1.8. And then from here, the first step is we're going to play around with the environments a little bit. So if you notice here, there's kind of a few magical things we can do in this REPL. The first thing is that we can get help using a question mark. So if I type in this question mark, so just question mark, it'll change the Julia to help. And then from here, I can, get the docs for a given function. So like print, it'll tell me what print's all about. And alternatively, I can look at the package manager, which is what I'm really interested in right now. So this is the right bracket. So over here, I'll do this. So just do right bracket, and it's just going to change from Julia to the environment I'm in, the package manager. So right now I'm in the base environment. So when I do status, press enter, it's going to show me what environment I'm in right now. So I'm in the base 1.6 environment, and it's going to show me the packages I have in that environment. So here we'll go back to our README in the Homework Zero repo. And what we see here is that the first thing to do is install iJulia. So what we'll do is we'll go back to here, and we'll just do add iJulia. Now I've already done this, so it shouldn't take long, and it says no changes. And then I'm going to press delete to bring it back to normal Julia. And I'm going to just type using iJulia and then notebook. And what this will do is this will open a Jupyter notebook in my browser. And then the next thing to do is I'm going to go over here and I want to clone this repo. So I can go ahead and I can clone this repo just by going code, download zip. And this is going to download a zip file. I'll click on this, it'll open it. And now if I go back to my Jupyter Notebook thing right here, I can navigate into my downloads folder. And then I'm going to open up the Julia Primer. So Julia Primer, this is a document I made that basically is going to go through a bunch of really basic Julia stuff. Just the stuff that you'll need to know to do the homeworks. In general, this is not the best intro to Julia document as a whole because it's not very performance oriented. We're just looking for nice, readable, stable code that's easy to debug and helps you learn the concepts. So what we have already is that we have this Julia intro, this guy Brian Jackson, who was a TA for the course last year. And he made a fantastic intro that goes through a bunch of really specific Julia stuff that will help you write great Julia code. And this document right here is not meant to replace that, but instead we're going to go through and do what is the absolute bare minimum that you must know to do these homeworks, hopefully in a way that keeps you out of trouble. So first thing we'll do is we'll do some basic path stuff. Actually, before that, to make sure everything's working well, on the top right corner right here, it's going to list your Julia kernel, and it should say 1.6.7. So if this says like Python 3 or Julia 1.8, something's wrong, and you might have to ask the TA for help. But basically, we're looking for Julia 1.6 right here. And if we started it the way that I described, this all should just kind of just work out magically. Okay, so first thing we're looking at right here, some basic path stuff. So I can use this at underscore underscore dir underscore underscore, and this will give me the path to the current directory of whatever file I'm in. And then I can get the the directory of this directory by just calling this dir name function on a path. And then I can make a path by just using this join path function where I join the directory with some made up file. So when I run these things, what we'll see is that directory, this is just a string. This is just the path to the homework repo I just downloaded. And then the directory of the directory is just one level up from that. So this is user Kevin Tracy downloads. And then this made up path that I have is the directory path. And then I appended on this made up file.jl. So the next thing is one great thing about Julia is it's super easy to interact with the package manager when you're not in the REPL. So if we're just in a Jupyter notebook, I can do all the package stuff I want to just by doing import package. And then to show that this works, I'll do package.status, and this will do the same thing I showed in the REPL where I'm just laying out the path to the current environment that I'm using, and then the things in that path. So here I just have 4 basic packages, and then what I can do is I can activate to ensure that I'm in the right path. So say I look at this path right here, and this is not the homework path. So this is not homework 0s23. What I can do is I can activate this dir directory, and I can activate this one that I want to, which in this case won't do anything because I'm already in the right directory. But this is how we activate a specific environment. And then once I'm in that environment, I can go ahead and I can add any package I want to. So here I'll add benchmark tools, which is already in this environment, but just to show you the syntax or how this works. So what might happen in a homework is that something may happen with an environment, and you go to download something, and you go to run the file, and the package you're looking for isn't in the homework environment for some reason. You would add it like this, or if you're doing a project and wanted to use your own packages. So here it's doing a bunch of downloading, making sure things look good. And then I'll do package instantiate, and what this will do is if I have things that exist in my environment, so packages on this status list right here, if I have packages on the status list that aren't downloaded yet, when I do instantiate, it'll go through and it'll download all those packages. So if you call instantiate and you already have the packages downloaded, nothing will happen. If you need those packages, it'll go and download them. Now the next thing to look at is how I use these packages once I load them in. So the first thing I can do is linear algebra is a package that's part of the standard library. So I have 3 different options on how I can actually import this package. So the first option is I can do import linear algebra, and this means that if I wanted to call like the norm function, I'd have to do linear algebra.norm. Alternatively, I can do import linear algebra as LA, and now I can do LA.norm. Or what's most common is I'll just say using linear algebra, and this will just basically take every single function in linear algebra that's been exported by that package and just bring it all into my current namespace. So now I can just say norm, and it works. And then I'll do using test. This is another package in the standard library. So now I can go on to some general syntax and linear algebra stuff, which is pretty much all of what this class can be all about. So, we can call our variables A, B, C, D, do whatever we want to. Here's an integer, here's a float. This is a uniform distribution between 0 and 1. This is a Gaussian. One thing to note that's different than Python is that I can use this right here to do an exponent. I don't have to do 2 asterisks. So we'll run this. First, let me just run this package. Okay, run this. This is everything you'd expect. And then one thing to note is that if I remove this semicolon, Jupyter will show the last thing as an output, or I can just suppress it if I want to. This isn't super important, but in a little bit, this will become more important. Another thing is that Julia code loves using these non-ASCII characters, which drives some people crazy, but I think is pretty cool. So what I can do is that I can type out this omega by doing this omega, and if I press tab, it creates the omega sign. And so what's common is I can do this with all the Greek letters, lambda, and there's a bunch of silly like emojis you can also do. So what's very common besides Greek letters is that we'll see dots sometimes. So, we do a lot of like derivatives in this class. So if I have like y, I do y and I do dot, and then tab and it adds the dot. Next thing is arrays. So we have 1D and 2D and higher arrays in Julia that all in the standard library. I can create a vector just using these comma, like the comma syntax. And I can create a matrix using, colons between the rows. So there's a vector, there's a matrix. And then we notice here that it outputted the last thing there. So I can suppress that output by just putting a colon. Suppress. So indexing, unlike Python, but similar to MATLAB, starts at 1. So vec 1, 2 will give me the first two entries of the vector. So 1 and 2. And then matrix, I can do, I need two indices here. So I do colon, this tells me give me all of the rows. And then 2 tells me give me the second column. And if you see here, I described 1, 2, 3, 4. So 2, 4, this is the second column. And this is a vector. So 2-element vector float 64. So I pulled a slice basically out of this matrix and it gave me a vector. And it's worth noting that if I do something a little different, so say I want the second row, I can say row 2, columns 1 through 2, and this will pull out the second row. But since I'm pulling out a 1D, piece of information, it will store it as a 1D vector. So even though this is technically a row vector, when I pull this thing out, Julia is going to simply just treat it as if it's a normal vector. Now, if I wanted that thing to maintain that shape of 1 row, 2 columns, I can just use reshape, and now I get a 1 by 2 matrix. Cool thing about these arrays, I can edit all of them. So vec 300, show vec, and then the first column, first row, I'm going to change to 20 on this one. And we just see that our original things that we had up here, we now edited. So the third element, this third, is 100, and then the 1, 1 spot of this matrix, I made it now 20. So it's worth noting that the indexing here, unlike MATLAB, we use brackets, not parentheses. Now for matrix multiplication, I can create two random matrices using this rand_n function. And if I give rand_n one argument, like in this case, it gives me a vector. If I give it more than one, it gives me an array. So here I do, it creates a matrices A and B. C is just A times B, and then D is A transpose A. And I can do transpose by just doing this tick right here. So transpose. I can equivalently just do this. But this is obviously more code and arguably harder to read. So we like using the tick in this class. And I can do matrix vector multiplication just like this. So here I'll create a random matrix A, random vector B, A times B, or B transpose A, just to demonstrate. And again, that suppresses the output, so it should be nothing. I can print out the size of these arrays. So A is a matrix, so it's going to give me 2 and 2. It's going to hand me out a tuple. And then the size of B, this is a vector, so it's just length 2. I can do the identity matrix in a bunch of different ways, but what's convenient is I can just use I if I want to. So if I want a 2 by 2 identity matrix, I can just do I with 2. And just like that, it works. Now, I can also just add, without specifying a size, I can just add this I value to an existing matrix that has a size that Julia will already know what the size is, and it'll just infer the size based on what is being added or multiplied with or whatever. It'll just work out. So here are two different ways I can create identity matrix. The types of these are different, but this shouldn't be super important. But basically, if you know the size, feel free to use this. If you don't, and Julia should know, you should infer it based on context, and feel free to just use I. The next thing we'll look at is how to solve linear systems. So this is super common in this class and in general, is that we'll see a linear system like AX equals B, where A is a matrix and B is a vector. So the first way, and unfortunately the worst way a lot of people solve these things, is you'll directly invert this matrix A and then multiply it with B. And you should never, ever do this. You should rarely invert matrices. What we should do is we should use this backslash command. And this is basically like a linear solve function that will take in a matrix and take in a vector, and it will factorize and solve the linear system in a nice, fast, and numerically stable way. So what we'll do is we'll use this test macro right here to make sure that the norm of AX minus B is very small, so very close to 0. And this just means that does, in fact, A times X equal B. And what we'll see is that it does, and it's going to say test passed. So this next section is somewhat more advanced usage. So if you want to use this backslash just to solve all your linear systems, that's totally fine. Sometimes if you know some structure about your matrix, like if it's like a positive definite, or if you think you're kind of worried about like the numerical stability of it, you can choose a different factorization than the default one that would be used. So what we'll do here is I'll demonstrate I can take this matrix A. This is a random 3x3 matrix, and I'll create a random positive definite matrix by doing this. These details aren't super important, but just know that the resulting A from this line is going to have all positive eigenvalues. And what that means is that I can factorize this with a Cholesky factorization. So here I have Chol factor equals Cholesky of A. And what this will do is that Chol factor is now going to be a struct that's going to contain the factorization in it. So if I want the actual lower triangular L, I can do Chol factor.L and give me this L. And what we'll see is that L times L transpose minus A is, the norm of this is very small. AKA this is matrix has been factorized correctly, and A does in fact equal LL transpose. So another popular option, and this will work for all full rank square matrices. So Cholesky will only work with positive definite. QR and LU, these will work with anything. And these lines just show you how to use the QR and LU factorizations, and then just making sure that they are in fact correct and nothing weird has happened. So we'll go run this. Everything looks good. And I can choose the factorization that I want to solve the system with. So here I'll create a right-hand vector b equals random 3, and I'll do is I'll solve ax equals b using all the different factors. So x1 I solve with Cholesky, and then QR, and then LU, and I'll just test to make sure I get pretty much the same result for all of them. And I do. Next thing to look at is ranges. So there's a bunch of different ways to do ranges in Julia. I find these three to be kind of like the only three that I would use. So it's common to do a unit range. This is our classic MATLAB syntax where it's 0, something, something. So it's 0 with a step size of 2 up to 10. And then, or I can do 0, 10, step 2, or 0, 10, length 6. So all three of these things, they create the same vector. They all create this right here. There's just three different ways to do it. So now we can talk about functions and types. So the first thing I'll go through is for loops, which is the same syntax as we'd have with MATLAB. So here I'll just do for I equals 1 to 2, and I'll just print the line. Here's the print line output, and then I to show the iteration. And see here, I equals 1, I equals 2. Now we'll go into some super basic type information. So we're really only going to use this as a way to kind of keep our code clean and ensure that we're not making any mistakes. We're not going to try and exploit a bunch of crazy Julia features here. We just want to use this as like a sanity check. So the way types are written here, here's A, which is going to be a length 2 random vector. And this is a type assertion. This is me saying, hey, this thing right here, it should be of type vector float 64. So we do this and we see that the type of A is vector float 64. And then this L type function, this tells me what is the type of the element of this array. So it's a vector float 64, and that means the elements are float 64. Now likewise, I can create a vector using this. So I can do b equals 1, 3. And now we see something a little different. So now we see this is a vector of int 64. So if I do the same type assertion, vector int 64, and I should feel free to add these things in my code whenever I want to just basically help myself find any sort of bug in the typing that I'm not really anticipating. So I'll just put my anticipated type here if I want to. You don't have to do this ever. This is never required. This is simply a type assertion. So here's some other basic types that we'll see. So here's like a 2x2 matrix of random numbers. So this is going to be a matrix float 64. This is a matrix of integers. So this is matrix of int 64. And then 4.3, this is just a float 64. And then this type assertion, this will fail if I do it wrong. So in my code, say I want some variable to be a matrix of a certain type, I can go ahead and add this right here. So in this case, I'm creating a matrix of floats, but then I do a type assertion where I say this should be a matrix of ints, which is not the case. So I do this and it says type assert error, expected a matrix int 64, and I got a matrix of float 64. Basically it's saying that like this thing is supposed to be floats, but I said it was supposed to be ints, so something's wrong here. I can change this to float 64, and now this passes because it's saying, yep, this is a floats, and I said it was going to be floats, so everything looks good. Next thing, which I love using, is list comprehension, which we don't have in MATLAB, but we have in Python. And this is super convenient for creating any sort of vector you want to. Here I'm going to create just a 1, 2, 3 vector of ints. I can also do vectors of vectors, which we love in this class and in Julia in general. Is that I feel it's much easier to keep track of indexing if I just have a vector of vectors. So here, each entry of x is a length 2 vector. And we use this all the time for like a trajectory. So if I have like a time history of a bunch of states, I'll have this big x variable, and every single index in that variable will be the state at a different time step. Now, if I want to convert this into a matrix, so like say I have a vector of vectors, but what I really want is a matrix where each column is a new vector, I can just use this right here. I can horizontally concatenate these things, and then when I do x dot dot dot, that's me just kind of, it's called splatting, but this is me taking the input, and each element in x I will input in this function as a new argument. So this is the same as doing hcat x1, x2, x3, which, the 3 elements I have right here, or I can just use the splatting operation and just deposit all of the entries of x as new arguments to the function hcat. And what this does is it just is going to line up these vectors such that they're all columns of this new matrix. Now this is helpful for plotting most of the time. So I can also do vectors of matrices if I wanted to. I could get even crazier just to show you kind of what we can do is that this can be any dimension I want. So here I have a 4-dimensional tensor right here that I'm looking at, which is probably not useful for our purposes, but I'm sure you could find a use case for it. Now we're going to look at some basic function stuff. So the function syntax is the same as it is for MATLAB. So function f, xb. The difference is that opposed to specifying the outputs in the function signature, I can just do return, like in Python. So here I'm going to take in x, take in b, and just return these two things multiplied together. And here I show that this thing is doing what it's supposed to. And now here's where I can use types if I want to. So you don't have to do this, but I do this just to keep my types straight and make sure that things are happening that I want to happen, like basically things are happening intentionally. So what I can do here is that I can specify type assertions for all the different variables in the inputs, and I can also add a type assertion for the output. So here what I'm doing is I'm saying I have this function f2, it's going to take an x, which should be a vector. Now before everything was like vector float 64 or vector int 64, here I'm just saying vector, so it can be a vector of anything. And then b should be a float 64, and it should output a matrix of anything. So not matrix float 64, not matrix int, it can be a matrix of anything. So these are super easy to write out. I feel that they make the code a little more readable to both yourself and other people, and they can help catch bugs if weird things are happening. So here we can see is if I change this here to be vector, it's going to fail and it's going to say, hey, I can't output a vector. Like there's no method matching this thing when I'm trying to cast a vector into a matrix. So here I'll just change this back to matrix, and now it works again. So like I said, it's super helpful because we can avoid bugs by specifying the sort of types that we want, but it also allows for something that the Julia people love, which is multiple dispatch, which means I can write the same function name, but I can have it for a bunch of different sets of input types. So here I'm going to have this function called print my type, and I'm saying that, okay, if this argument A is float 64, I'm going to print, thanks for inputting a float. So I do this. Now if I send this function print my type, if I send it an integer, it's going to fail. It's going to say, I can't find any sort of function print my type where it's expecting an int as the input, right? I wrote one function definition here where a is a float, but I haven't written anything with an int. So I run this, it says, no method matching. So what I can do instead is I can now just write a new function, print my type, so it has the same name as this one, right? These functions are the same number of inputs and everything. But now I just specified that, hey, if the type of A is an int64, call this function instead. And here I say, thanks for inputting an integer. Now this is super convenient because it means I can do operator overloading. So I can write, this is how like multiplication works, right? I can define a multiplication method for numbers and vectors and matrices and all these things. I can overload an individual operator or an individual function with a bunch of different definitions based on what the types of the input are. So now I'm going to go into some things to watch out for. So there are definitely more things that can cause bugs in Julia than there are in MATLAB. So this is one of the reasons that we want to use as much MATLAB looking Julia in this class as possible, but it's worth noting that there's a few things that are fundamentally different that we're going to have to be super careful of. So the first thing is the difference in global and local scope. So everything I've done so far in this document has been in global scope. And this means that, if I define some variable x right here and I do, some function my f, even though there's no inputs here, I'm somehow going to print f. So what we'll see here is that I'm printing x even though I wasn't passed in. So like I didn't tell this function my f anything about x, but because x is a global variable, every function, everything has access to this. So print x, it showed up no problem, x equals 4.6. And this is kind of scary because it means that these functions are no longer pure functions. And by a pure function, I just mean that it only has access to information that's passed in. And in my experience, it's much easier to debug functions that are pure functions than things that rely on global variables. But it's also performance-wise, this is terrible to do. Code safety-wise, this is bad to do. Like there's really very few reasons to actually do this, with the exception of if I make it a constant. So unfortunately, in this function, I could edit x if I want to. So not only do I know about x, but now I can edit x. What I can do to kind of avoid that is I can make any global variable, which may happen sometimes, is I'll make this thing a const. And what this means is that this x const, it can be used by every function. It's a global variable, but it's not mutable. Like I can never change this value. And if I try to, Julie's going to complain. So we'll use this every once in a while in the class, but basically if there's ever a global variable in this class, it should be a const. We should have no just kind of normal floating variables like x right here. So now what we can do is that we can kind of test what it means to have local and global scope. So what I'll do here is I'll have this function called test local scope. And here I'm going to try to print out a global variable and then print out a local variable. And then I have const, a global variable. And then what I'll do is that I'll wrap this little thing I'm doing inside of one of these let end things right here. And what this means is that anything that happens between the let and end is going to be in some of its own local scope, which will avoid it from polluting the workspace with a bunch of global variables. So I call this, and so I was able to call test local scope. It called this function right here. It went to the line 8, and it said here's global variable, and it printed out the global variable, which is 23. And then I say here's a local variable, which I defined right here, and it's basically saying like I don't have that, like local variable is not defined. So here I showed that here's a global variable, here's a local variable, and this function was able to, even though it has no inputs, it had access to the global variable, but not to the local variable. So this is why we do everything in this let end in this class. If we're doing just general scripting stuff, is that it basically stops us from creating global variables, which can be bad. And here I'm going to show that again, x is a global variable. This function f, yeah, I know about x. X is 3.4. So this is another way I can use to determine if like a variable has been defined. This isn't super important though. So the next thing to look out for that we don't see in MATLAB is that functions can modify their inputs. So this is true in Python. I can take this input, which I'll specify should be a type vector, and I want to change the second element of this thing to be 140. So I do things in a let end again, just to make sure I'm not polluting my scope. So here I have input is 5.9, and I'm going to print out what the input is before, and I'm going to mutate it with my mutating function, and I'm going to print what it is after. So before it was 5.9, and then I called this function right here where I changed the second element to 140, and then after it's 5.140. So what we can see here is that this input, which I defined here, it got modified by this function. And it can be sometimes tricky to debug code if all the functions are modifying a bunch of the inputs, which is why in this class we're never ever going to do this except for very rare occasions. So we're never going to try and change the input of a function. We're never going to mutate. But if a function does do this, it will let you know about this behavior by adding an exclamation point at the end of the function name. So if you see a function with this exclamation point like we have here for a mutating function, this tells us that it's going to change something about the inputs, which again, MATLAB can't do, but Python can. And so here I'll demonstrate how this looks for more generic functions. So sort just takes a vector in, it's going to sort the vector. So here I have 4, 1, 3, 2, so it's clearly not in order. I go and run this, so 4, 1, 3, 2, this is my original version. And then here I say, here's a sorted version of it. So I call sort on x, and it's going to print out 1, 2, 3, 4. Looks nice and sorted. But then when I go and I print out x again, x is unchanged. So I used sort, and that took in x, and it outputted a new vector that was ordered 1, 2, 3, 4. Alternatively, I can call this sort function with the exclamation point, and this will mutate x. It'll modify it in place, and it will rearrange the elements such that it's sorted. So here I call the sort function, and then now when I print the modified x, I see that this thing is actually sorted now. Another cool thing to know is that I don't have to special case functions for scalars or vectors. What I can do is I can use this dot operator to apply a scalar function to everything in a vector. So here, absolute value of 3 gives you 3. I'm going to create a random vector of length 4, and I'm going to show x here. So here's x. I have some positive, some negative numbers. And then if I do abs x with the dot, it's going to apply the absolute value function to every element in this vector. So now if I look, before it was negative 0.22, now it's positive 0.22. So abs got applied to all these things. And same works for a matrix. So it works for both vectors and matrices. It also works for vectors of vectors. So here's this function, or here's this x, which is a vector of vectors of length 2. And what I'm going to do is I'm going to call norm, which is going to give me the norm of the vector, for each of the vectors inside of the vector x, if that makes sense. So here I have x. Here's the first entry is a vector, second entry is a vector, third entry is a vector. And if I call norm dot on this, I'm going to go through x, and I'm going to calculate the norm of each of these 3 vectors, which is super useful. So now I'm going to look at some plotting examples. So plotting in Julia is good, not great. It's definitely good enough for this class. So I'm going to go through some super basic things that we'll do. We're not going to do anything crazy in this class. We really just want plots to make sure that, are things happening the way we expect them to. It's like a general sanity check. So here I'm just going to plot sine function. So I call plot, and then here's classic x, y, and then label. This gives me this label right here. X label, y label, x limit, y limit. This syntax right here is like 90% of what you'd ever need. So here I can do multiple plots at once. So I do plot, and I create the same plot as before. And now I use plot exclamation point, and this is going to modify my existing plot. So now I do x cosine, and then I'll do a scatter plot on top of it, where I just plot a bunch of random points. So these examples will be nice to look at if you want to make some of your own plots for like a project or something. These are just super simple templates we can use. And here we say that it plots sine, plots cosine, and then plots a bunch of random scatter points. So now we're going to do something that we're going to do in almost every single homework, which is I want to plot a trajectory. So I have this thing, time vector, so it's between 0 and 10 seconds, and then I have this trajectory that I create, in a fake way using like this exponential function. And what you see here is that for t in time vect, so time vect is an iterable, and t is just all the individual entries in these things. So this is me using list comprehension to create a vector of vectors right here. I'm then going to convert this into a matrix using our hcat and splatting trick. And then I'm going to go ahead and plot this with 3 different labels. So what we see here is that I have 3 different elements of this vector of vector. I converted to a matrix, and then I plotted it, and here's all the labels for it. X label, Y label, stuff like that. So this is super common. So say I have a controller, and I want to stabilize all the variables of the state to 0 or something. I can plot the state history like this, where each of these new lines is a different element of the state. And I can start with the vector of vectors, and I can spit out a plot that looks like this that shows me what happens over time. And now I'll do like a little bit of a code example to kind of show like how we can piece some of these things together. So import forward diff is fd. This is me taking a package forward diff and bringing it into the namespace under fd. I'll define just a super simple function for a first order Taylor series that wants a function inputted f. It wants a linearization point x bar, and then it wants the variable to be, or the place to be evaluated at x, and I want to output a float. And it's worth noting that to create this x bar, you do x bar and then tab, and it makes it. So here's this function, super simple, and I have x from -6 to 6, and y is sine x. I'm going to linearize this, so my x bar is going to be some random point, and then I'm going to create the Taylor expansion using list comprehension. I'll say, all right, call first order Taylor using function sine, linearization point x bar, but call it at each of these points x. And now what we'll see is that when we go to plot this, that I'm going to have a plot of here's sine x, here's the linearization point, and as we'd expect, the first order Taylor series is tangent to the function at this point, and it's just a line. Okay. So one last thing that I forgot to add in here that we're going to use all the time are named tuples, which I think are just the most convenient thing ever. So what's extremely common is I'll do like params, and I'll store all my parameters in a named tuple. So I'll have A equals B, C, and here's params. Now the cool thing is that this lets me pass in variables like this, params.a. So we use the dot syntax to print these things, which is nice. And then what's important is that these things are immutable. So if I tried to do, it's gonna be like, nope, I can't do that. You're trying to set the field of a named tuple without changing anything. So I use this all the time for simulation. So imagine if I'm trying to simulate some robot and I have, fixed geometry, like I know my inertia matrix, I know the mass. I'll just shove all those parameters in a named tuple, and I'll pass that into the function and evaluate it. So this is a super quick rundown on Julia. I'm going to post all this stuff. This is actually currently inside the Homework Zero repo. Feel free to go dive into the Julia intro, which has another video by Brian, which is, again, amazing, and there's tons of info there. There's actually even, what's worth looking at is there's a great cheat sheet in there. So here's this video, and then text cheat sheet, text cheat sheet, which has a lot of the stuff I went over right now. You can go through if you ever trying to, I know how to do this in another language. How do I do this in Julia? It's probably listed somewhere in here. And in general, all the stuff is super Googleable. There's a bunch of great Julia documentation. And in general, these homeworks are going to be doing things that are so simple that almost everything you need to know should be in this Julia primer right here. So the goal of this class, again, is not to have you guys writing extremely performant code. We want you guys understanding what's going on. And we think that doing that in Julia is the best way to do it. So going back to the homework, the way this works is that we'll have two Jupyter notebooks here, so Q1 and Q2. So go back to Jupyter, open them both up, Q1 and Q2. And here I use all the stuff that I just laid out. So here's how to do the environment stuff to make sure we're in the right place and we instantiate it. And so this question is going to take you through how to use, basically how to form a derivative in Julia and the two different packages that we'll use. And this homework is super simple. You just got to go through and fill some stuff out and just make sure you guys actually read it, because undoubtedly you're going to have some of these bugs as you go on with the homework because we're doing a lot of diffing. And if you have the bug and you come to office hours, we're happy to help you, but you could definitely save yourself some time. If you ever get stuck on diff stuff, go back to this homework and read through it again, and hopefully everything should be clear. And then the second thing is going to be on Newton's method, which is surprisingly simple, but definitely can be done incorrectly. And it's really important that we're pretty solid on Newton's method. So this is going to go through, do some basic examples in 1D and in multiple dimensions, and then also for optimization. So, we've all seen Newton's in different classes. We're just kind of going to formalize the sort of notation we want to, and how to do this in code, how to do this specifically in Julia. And so these ideally should both be super easy to fill out, make sure everything's working, and then once you're done with the homework, you'll do File, Print Preview, and then Print. And this is just an easy way for us to make a PDF of this document, and then from here we'll just submit it on Gradescope.